All right, everybody. In an effort to stay on time, we're going to start immediately now. That way people watching the live stream also know when to tune in. So if you could come back in. If you remember this time yesterday, Dimitri was talking about parsing. And so on the topic of recursion, we have another parser talk coming up from Bastiaan, who actually is a naval architect. So he brings a different kind of expertise to the stage. So please take your seats and give him a round of applause.
Thank you very much. Thank you very much. So this is another talk about parsers. Pact is a parser generating library. And everything Dimitri told about Pact yesterday is true. Nevertheless, I think I have a few nice things to say about Pact today. What this talk will not be is a complete presentation of all its features. Instead, I'm going to talk about some improvements I made so it does the things that I need. I'd like to give this talk some context, and therefore I'll start with a short presentation of what and whom I work with and why we are interested in DE. So at my core, I am a naval architect. I was educated to design ships and other floating structures. I believe I'm the only naval architect in this room today at this conference. I'm going to show you some boats because I can't help it. But I think we'll be able to find some common ground in the end, I promise. I spent most of my working hours programming professional ship design software for a company called SARC in the Netherlands. The main focus of SARC is to make sure that ships are designed and operated with sufficient stability. To give you an impression of the matter we are dealing with, I'm going to open with an example of what can happen, and it did happen in this case, if you don't use the kind of software that we produce. It is about an accident, an event that I'm sure the German people in the audience recall, because it was in the news a lot over a long period of time. In the winter of 2011, this chemical tanker was on a journey down the river Rhine, which is a major European shipping artery. It is a very typical ship on inland waterways. It was loaded with sulfuric acid and 96% purity. After having traveled for more than 7 hours without incident, at 4 hours 42 in the night, it navigated a tight bend in the river. This is a simulation of the physical mechanisms that were at play, and up to the right is a recording of what traffic control was seeing on their radar. This is true time. This is as fast as things were happening in real life. At this point, people are fighting for their lives. From the crew of 4, 2 were swept overboard in pitch darkness. One of them was saved by a passing vessel, heavily injured. The other one was never found. He disappeared. You see, the radar echo there almost completely vanished. With its bottom up, the vessel drifted downstream past 4 other vessels, ramming one of them, until it stranded 1 mile further downstream in this position. A third member had been in the living quarters during the whole event and could be saved afterwards through a crack in the window, also heavily injured. The fourth member had died in his cabin. His body was recovered when the ship was salvaged. Somewhere between 1.5 and 2,000 tons of sulfuric acid ended up in the river. And it took 32 days before they managed to remove the wreck, which caused chaos and heavy delays for hundreds of vessels, and the implications for the surrounding industry. A catastrophe of this, with consequences of these proportions, had never happened before in European rivers, and it caused a big demand for our software, I can tell you. Which is not only a good thing for us, but it helps improve the life expectancy of sailors. We do bigger ships as well. On the other end of the scale, you have this giant ship, which we delivered the so-called loading computer for, which enables it to safely perform massive operations. It is designed for the single lift installation and removal of large oil and gas platforms and the installation of record weight pipelines. It is the world's largest vessel, not the longest, but the widest and also the one with the biggest displacement, 900,000 tons. It has tanks so big that we had to make changes to prevent overflowing our data structures, our data types. A loading computer runs tailor-made software and is installed on board after the ship has been built. The biggest part of our code base concerns the design phase, though. It comprises a whole suite of tools, and I'm going to show you just one example because I personally spent most of my time on it, and it produces the nicest pictures. This is our geometric modeler called Fairway, a program for the computer-aided design of the shape of ship hulls. What you see here, the GUI is written in C++ using Qt and Coin3D, but that is an exception. The kernel of Fairway and all other modules of our software is written in a different language. Who likes to have a guess what that language is? Some of you know. Actually, it is Extended Pascal. The company was founded in 1980, and that's where it started to use Pascal. Pascal is a language that is about as old as I am, and was popular at technical universities and colleges in the 80s and 90s. Early Pascal was not without flaws, which caused various vendors to make incompatible extensions. So when a new standard was defined in 1999 and 1990, called Extended Pascal, that addressed most critiques, Sark naturally upgraded to the first compiler that implemented the new standard, produced by Prospero Software in England, expecting that this would be a safe choice and other vendors would follow. Sark has been very productive with this choice, but history has not developed as we expected. Prospero remains the only commercial implementation of Extended Pascal to have ever existed. Its creator has retired long ago, and Prospero Software and its compiler have vanished from the internet. There exists an implementation that is called the GNU Pascal compiler, but maintenance has stopped many years ago, and it can only be compiled against an old version of GCC. So to speak in metaphors, we feel that the ship we are on has stopped dead in the water, and it is leaking. And although not directly life-threatening, we are looking for ways to convert our code base to either another dialect of Pascal or to another programming language altogether. This should largely be an automated process, as our code has accumulated to roughly 500,000 lines of code, and that's excluding the C++. V is one of the contestants, I'm happy to say. Let's look at some of the reasons why. We love nested functions, to the point that we can rule out all other languages that don't support nested functions. We use nested functions all over the place. In fact, we pulled some assembly tricks to save and restore stack pointers so that we can use nested functions as Windows event handlers. And the delegates will let us do that without assembly. Next, compilation speed. We are spoiled with the compilation speed by Prospero. It's amazing. And I hate how long it takes to compile the C++ parts when I make changes there. And apropos C++, I only bear writing C++ because of the conveniences the Qt library gives me. And I survive because I have read the rules by Scott Meyers.
Oh, if I want to make a quick comment.
Yeah.
Nested functions indeed came about because of my experience with Pascal many years earlier.
Wonderful.
So I'm not surprised that you like that part of it.
Wonderful. And you kind of have to be an expert in C++ to write decent C++. And for people who have to be experts in other fields like naval architecture, it is just not a good choice. Other bonuses that lure us over are the garbage collector. You know, I think the garbage collector haters get way too much screen time. I can only see advantages a garbage collector would bring us, not to speak of the language features and library features that the garbage collector allows. Experimentation. D and its standard library seem to be designed to encourage safe experimentation. An example. For performance reasons, we implemented memory pools for many of the data structures used in Fairway. This needed to be done manually, and although it did boost performance, we didn't know that until after we finished implementation. Had we used D, STD experimental allocator would have offered us free list right out of the box. Not only that, we could easily plug in different allocators and pick the most efficient one. Parallelism. Parallel for each is just unparalleled. Some other advantages that I'm sure would find good use in our software are contract programming, safety, and unit tests for obvious reasons. Templates. This would certainly be a new concept just because Extended Pascal doesn't have them, but D templates are so clean that I would have no problem introducing them to my colleagues. And they will be essential in representing some generic constructs that do exist in Extended Pascal. Many other small features or conveniences, of which I shall mention just one example, WYSIWYG strings. The strings where you don't have to escape anything. They are very nice, and Pact certainly make good use of them. Now on to parsing. If you're thinking about translating 500,000 lines of code, there are several options, which all need some degree of investment. But I thought, if I'm going to advocate D, I might as well try implementing the parser in D as a test, so to say. So I went over to codedlang.org, and nowadays there are exactly 30 hits in the parser and lecture department. A few fewer when I looked, but anyway, I landed on a project that stood out in that it is amazingly well documented. It's called Pegged, and it is written by Philippe Sigaud, who made his first commit in 2012. And if I say well documented, I don't mean only documentation. I mean a wiki with currently 28 pages containing an extensive tutorial, examples, and background information. And the biggest selling point of all was that it lets you define a grammar as a piece of text that has exactly the same structure as the ISO standard document and almost the same syntax. The above is an excerpt from the standard. The lower is the corresponding piece in the format that Pact supports. This is a great advantage because it means I don't need to manually reconstruct the grammar in some other format, which would almost certainly be a source of errors. And I didn't want to spend much time on the parser because translating language constructs will be the actual hard thing. Pact allows me to just type over the grammar rules from the standard document, and it will generate a correct parser for me. Or so it appeared. I will tell you about the difficulties. Let's start with an example from the Pact homepage. This defined a small grammar for basic arithmetic expressions. It has operator precedence, so multiplication and division bind stronger than addition and subtraction. I'm not going to take much time to explain you the format. You should follow the tutorial if you're going to write your own grammar, but it's pretty obvious. Star means 0 or more of the thing that comes in front of it, plus 1 or more. Parentheses are used for grouping, slash for optionals, like it's taking only one of parents' next number of variable, and sequences do the opposite thing. We have a character range there, and tilde is used for fusing matches. So if I match a 4 and then match a 2, it fuses them to 42. A more complete coverage of the Pact syntax is in the tutorial. Now, when I mix this in at the top, it gives me a parser that I can call as a function. one here, which parses the input that I give it and gives me a parse tree. And the parse tree is a struct with a toString member. So if I write it out, there I get this parse tree. So it doesn't only give me the struct, it also prints out all the children. So each line represents a rule which starts with the name, then come two numbers. The first is the starting position, and the end position. In between, it found its matches, which are given at the end. Now what? We have the parse tree of an arithmetic expression, but how to use it? This is an extension of the same example. I just reduced the font size of what you've already seen. And instead of writing out the parse tree, I wrote out the result of a function that I call on the parse tree. And the function returns a float. And the grammar had just two leaf nodes, which are handled here. It's the only point where the function doesn't call into itself. Number, for example, has the number in string format as its match, and it's just converted to float. Most other rules just have to evaluate their children. Sub and neg, almost the same, but they negate the value. Diff gives the quotient of the value. Term gives the sum of all its children. Factor gives the product of all its children. And this is executable code. If you run it, you get -3, which is the result of the expression. I've noticed that I've used the enum here. So if you want it, enum will get you the parse tree at compile time. And actually, enum is up there for the parse tree, and this is for the result. So everything that is done at compile time. But I should add, this is really cool and all, but grammars generally don't change all that often. And Packrat has no memoization at compile time, so you mostly want to generate the parser as a module and parse at the real-time runtime if you can. Marvelous. But how is Packrat able to pull this magic off? As a casual Packrat user, you don't need to know this, but in a nice demonstration, it is a nice demonstration of the powers of D, so let's have a look. Consider a rule like this, which means A is produced from B, which is another rule, followed by a C, then one or more Ds, and optionally followed by an E. This can actually be implemented in D like this. And this is somewhat simplified code as Packrat produces, so it's generated by Packrat. At its core, Packrat has predefined parser combinators to construct parsers for the rules in the grammar definition, just as in prior, which were introduced by Dmitry Oshansky. So you can see how this is equivalent. We have AND, which covers the sequence B, C, one or more of Ds, and optional an E. It's very straightforward. So how do we get from a rule like you see up there, to code down there? Well, you do that with a parser. The parser generating parser can itself be generated by Packrat. Before I show you how that parser generating parser was constructed, I'll have to explain where Packrat got its name from. Packrat is based on the PEG formalism introduced by Brian Ford of MIT in 2004. The full article is linked from the wiki. PEG stands for Parsing Expression Grammars and defines top-down recursive descent parsers. It uses prioritized choice as opposed to unordered choice, meaning that it accepts the first option that matches and disregards any remaining options. And greedy operators, meaning that repeated elements consume as much input as they can. And together with memoization, this produces parsers that parse in linear time. Brian Ford actually provides a parsing expression grammar that formally describes its own syntax. This is roughly how PEG was bootstrapped. So we wanted a parser for PEG. The way to get that was to write a parser for each rule on the left by hand, like we've done before. And with that set of parsers, grammars, including this one, could be passed into a parse tree. The real work was then to write an interpreter evaluator for the parse tree, like we've seen in the arithmetics example. Instead that it doesn't evaluate an arithmetic expression, but it generates decode that implements the rules of the grammar. So essentially automating step 2 there. So whenever we want to extend PEG'd, that involves changing the grammar, and the PEG grammar has changed quite a bit, we only need to adjust the PEG grammar on the left, regenerate the PEG parser, and implement the new parser functions that correspond to the extensions. PEG is self-hosting in this way, and like Philippe writes in the wiki, most of PEG was written by the decompiler, not by a human being. Now, users need not remember all this, but it explains how PEG accomplishes its magic. So having found this extremely powerful parser generator, I thought, this is good, this might just be going to work. And I happily set off writing my transcompiler. For this, I typed over the sections of the standard. The total extended Pascal grammar now counts close to 600 lines, and gradually increased the subset of the language that I could parse. It was a lot of fun until one day my parser crashed consistently on certain input. It was only then that I learned that the extended Pascal grammar is left recursive, a term that I hadn't heard of before, and that most PEG parser generators do not support, and neither did PEG. It was a real bummer, and at first I thought this was a deal breaker. But I had had so much fun that it kept itching, and I started researching, and eventually I found some recent publications that proposed a solution. And I'd like to tell you about it. First, let me present you the problem. Consider a fictional language that consists of n, n plus n, n plus n plus n, etc. This can be parsed by a rule like this. So it starts to look for a plus n. If it can't find that, then it wants an n. If it does find the n plus, then it wants it to be followed by either another n plus and r, or an n, etc. PEG will translate this to this decode roughly like this. So this is working decode. You can find it in the examples directory, which is linked from the talk page at the DConf homepage. So if you run this, you get a parse tree like this, as expected. And you can see here that it recurses. It does OR again, but this time on a different position in the input than the first OR, which starts at 0. But there's another way to write this rule, and it also describes the same language. Watch carefully at the rule in the top right. The literal and the R swap places, and the N and plus in the literal swap places. OK, the same swaps take place in the decode. The rest stays the same. Run this. Ow. Slap in the face. When this was still a problem, this could happen without warning, and whether or not it happened was dependent on the input. and users were left alone to blame the library or the language. But what happens here is obvious, of course, if you look at the code. I'm sure all of you spotted this immediately. R calls into itself with the same argument, that is trying to parse the same input at the same position. And it keeps on trying until it miserably runs out of stack space, almost instantly. Very nasty. So this phenomenon in the rule that we have just seen is called direct left recursion. This rule is also left recursive, but the recursion hides behind another expression that will succeed on any empty match. In this case, S is optional, so if S doesn't match, it goes on to try R at the same position, and you have the same situation as above. Hidden left recursion can be more obscured. From the rule R itself, it's not obvious that it left recurses, but when S is tried and A, B, C doesn't match, then the star is tried, any number of these, including 0. So OK, S succeeds on empty match, and R falls into the recursion trap. You can imagine that there is no end to how deep left recursion can be hidden in a grammar. Does this recurse? Yes. R tries T, T tries GH. If that doesn't match, it tries J. J tries K. If that doesn't match, it tries R, and we are back. And of course, there's hidden indirect left recursion. Is it complicated yet? Sometimes it is possible to eliminate left recursion from a grammar by cleverly rewriting rules and introducing intermediate ones. But this affects associativity, and to my knowledge, it is not possible if there are multiple interlocking cycles of left recursion. Consider this input and a matching grammar like this. How many cycles of left recursion are there? Well, you have E calls into F, which calls into E, straightforward. Same thing, G calls into H, calls into G, also straightforward. We have E to F, but if the first option of F doesn't match, it tries G. G tries, if the first option of G doesn't match, tries E, and we're back at E. And they interlock, so from one point, it can left recurse in multiple ways. Another example, and this is actually not it can be observed in grammars of existing programming languages. So on to the cure. Thanks to the research of these guys, we have a cure. Links to full-text PDF can be found in the wiki. They present the concept of bounded left recursion, which involves two elements. Firstly, a way to control recursion step by step, and secondly, a condition for when to stop recursion. Let's look at the second element first. Let's loop back to our initial directly left recursive rule. And we are going to write out the recursions and consider the matches at each recursion. For this, it makes sense to index R with the number of recursions. We start by defining R-1 to fail right away. This actually causes recursion to stop, so that R0 evaluation of the rule without recursion makes the first option to fail and reduce to the second option. R1 references R0, which after substitution gives you this. Next, R1. Yeah, right, I'm out of sync here. So R1 references R0. If you substitute that, you get R1 will want to match n plus n or n. Next one, R2 references R1. If you substitute that, you get this. And this one's actually n plus n or n. Now let's see what happens when I let this recursive rule loose at the input n plus n, the middle one at the top. If I do not recurse R0, I can only match the first n. Recursing once, R1 matches the whole input n plus n. Recursing once more, R2 can only match the first n, no more. When you add another recursion and try to match the last example, n plus n plus n, you will see that R2 matches the complete input, but R3 matches only the first n. Medeiros et al. Showed that when in left recursion, the part of the input that can be matched increases with every recursion, but only up to a certain depth. Recursion beyond this depth matches a shorter part before increasing again up to the maximum. So, recursion should stop when the length of the match stops to grow. Now back to the first element. Controlled step-by-step recursion. We start again with our generated parser and highlight the part that, well, yeah, we highlight the part that actually does the parsing. Okay, we're going to add a few lines of code here. But the part that does the parsing stays at the same place. This is some pseudocode. This doesn't compile. But for starters, it's easier. And I apologize if this appears very easy to you. I don't mean to insult you by feeding this with a baby spoon, but apparently this is so complicated that almost no pack parsers implement this. So bear with me. We start by initializing a static variable representing the previous iteration with a value that indicates that we haven't recursed yet. Then we assign to the current parse result a failed state representing r minus 1. Next, we write down the current parse, the parse result as the result of the previous iteration when we recurse. Now we start recursing. We note down the result for the next iteration with actually calls back into R. Because pref is not none anymore, the value of the previous iteration, fail, is returned immediately. So result gets to match the first n, which is R0. Now we check whether this iteration still grows the match. The length of n is longer than a failed match, so pref and current take over the value of the resulted parse, n. Next iteration. R is evaluated once, returns n immediately, and result gets the match n plus n. Still growing, etc. Until the newest result does not produce a longer match, and we are done. Static variable is returned as static variable is prepared for another left recursive evaluation, and current is returned as the correct parse tree. Notice how this implements the manual progression that we did before. Also note that the function r is not actually called recursively I times when r is evaluated with a recursive bound of I. The bound is increased step by step, while the previous step is kept readily available. So complexity is still linear. Now in the transition to the next slide, you'll see the pseudocode replaced with real D code. Nothing dramatic. The advantage of not assigning none to the static parse tree is that using an associative array, I can actually go into a second left recursive call later in the input when I'm still in left recursion from a previous position. Now zoom out to the complete source file. Press compile, and we get a proper parse tree. No more signal 11. All it takes is an extra dozen lines of code. And for comparison, the output of the right recursive parse tree from before. which is different as expected. Very nice is that this cures all kinds of left recursion. The only things that needed to be done is analyze the given grammar and identify all left recursive cycles, then select one rule in each cycle and equip it with the bounded recursion implementation, and make sure that memoization is paused while you are in left recursion. Otherwise, it prevents the match to grow. And all this is fully automated. The user need not worry about any of this. Pack just does the right thing. All it does is leaving a note in the generated code stating the left recursive cycles in the grammar. These are all cycles present in the extended Pascal grammar. And as you see, they're all indirect and intersecting. So from now on, I think everyone that maintains a parser generator in Dub knows how to support left recursive grammars. A short slide about other PRs that I contributed. Interactive HTML5 output for large parse trees, where you can collapse and expand subtrees. Case-insensitive matching of literals. Pascal is a case that has case-insensitive keywords. A tracer compile option which generates gigabytes of log files in case you need to see exactly what's going on with your parse. Next, it appeared that the prioritized OR from Packed was not sufficient for extended Pascal, because at some places you don't actually know what rule is going to produce the longest match. So therefore, I implemented longest OR. And the extended Pascal grammar is added as an example to Packed. So status of the translating compiler at the moment, it constructs parse trees for large extended Pascal's files, which includes comments and white space, because I want the translated source to be documented as well, and maybe preserve some formatting. I don't use a symbol table. I don't plan to either, which means that at some places I, for example, can mistake a variable access with a function access. Because in Pascal, a function that doesn't take any arguments, doesn't have parentheses either, so you don't know whether you are evaluating a variable or function actually. But I don't think that will be a problem, because once translated, D will just do the right thing. And there is no focus on speed. All I care about actually is correct translation. If it takes a week to translate all our code and does it correctly, I'm very happy. I'm not going to do it again. What remains is to verify that all extended Pascal language constructs have a matching D equivalent, and then implement the translation. I think I have 1 minute or so to show you some real code. We have seen several slides of code, but I'd like to get focus back on how much you actually write. Let me see if this works. Doesn't. The link doesn't work. Let's see if I can get you here. No, I should have prepared that, I think. Go and look for it yourself. But the conclusion actually is that I do need to define the grammar, but that's actually not a job I had to do. It's just copying it from the standard. And the only thing I need to do to get a parse tree is a single line of code. You can see it in the examples in the Git repository. So thank you very much.
So this project to translate, as it said, 500,000 lines of code, right?
Mm-hmm.
So pretty daring project. Do you have much idea of how you can verify that it works?
No, that will be the interesting part.
Okay.
As I said, I started writing the transcompiler right immediately before I hit the left recursion snag. I have good hopes that it's going to work. Yeah, some interesting problems. Stefan.
Having some experience with transcompilers, you really want to think about adding a symbol table. It's going to save you a lot of headache later.
Why?
Because there is not always the ability to do a literal translation. You cannot just parse some things and translate them directly. There is always some change in semantic, and although you're probably not aware of this right now, I can guarantee you that there are corner cases which will make you pull your hair out if you don't think a little bit about implementing things like symbol tables right now, because if you don't do this as early as possible, you are going to be a very unhappy person.
Fortunately, extended Pascal isn't as complicated as other languages, maybe most other languages. But I'll drop you a line if that hits me.
Just curious, how long does it take to compile your extended Pascal grammar? Because in my experience, pegged can be a bit slow.
The compilation of the grammar, I don't actually remember. But it isn't really a problem for me, but because once it's done, it's done. I compile it to a module, and I don't have to do it again. I do it very few times, only when the grammar changes.
Do you have any expectations for challenges related to how memory allocation might change between extended Pascal and D's typical behavior?
Yeah. We do manual memory allocation, new and dispose. I think that will translate directly to malloc and free.
Any other questions from the theater audience? You can check the chat. I don't think we had any questions, though. Doesn't look like it. Well, if there's nothing more, can we give another round of applause for Bastiaan?
Thank you very much. It's been an honor.
We have a small announcement before we go to lunch early. The hackathon is slowly taking shape, but needs more input from everybody who is attending it, and also from the people who are watching the live stream. So if you want to see things in the community change technically, or maybe more personally in the sense of how everyone works together, please take a look at the deprogramming language Twitter post, as well as the DConf post. Both of them have a link to the forums, I believe, where there is a thread going where you can contribute your ideas about what should be worked on, what's most important right now for the community. And again, that can be technically, but also maybe that's related to process or resources. So take that seriously and take a look, because it's not every day that everyone is physically together, or a large part of the community is physically together. So take advantage of that in preparation for tomorrow. And with that, please enjoy your lunch. We'll see you back here at 2:30.